are the lowest whole number ratios of atoms in a compound. And many times we're able to analyze a compound to determine what percentages of the different elements that compound's made from, what percentage in mass for each element. So back in the early times of chemistry, they were able to take this information and they would be able to calculate the percentages. In fact, you're going to do this in lab coming up. We're going to burn some magnesium and determine the chemical compound for magnesium oxide. And they're able to use this based on percentages and calculate what the empirical formula is, or the whole number ratio of atoms. Again, we're going to be counting atoms based on their masses. Let me show you how to work this mathematically. Here's our steps that we're going to take. We're going to start with percentages. We don't always start with percentages. Sometimes we will start with grams, or sometimes we may even start with moles. If we start at a different place in the process, then just jump to that place. So in this case, we're going to start with percentages, and I'm going to work the whole thing through for you. What we want to do first is take the percentages and change them to grams. Then we're going to change the grams into moles. And then we're going to take whichever one is the smallest of either the oxygen or the nitrogen, and we're going to divide both numbers by that smallest number. And that should give us our whole number ratio. Sometimes adjustments need to be made if you end up with a fraction. And I'll show you how to do that. So, how are we going to change things to grams? Well, because we're dealing with a percent, it doesn't really matter how much of the substance we're going to start with. So it's recommended that we just start with a 100-gram sample. If I start with a 100-gram sample, then 63.16% of that 100-gram sample is just going to be 63.16 grams. So when I say this phrase, change it to grams, literally all we want to do is just take the percent and turn it into grams. I'm going to do that for the nitrogen. 36.84 grams of nitrogen. Just change it to grams. Next step, let's change it to moles. This is what we've been doing in the other videos. So I have 63.16 grams of oxygen. I'm going to set this up with my dimensional analysis. I'm going to put 16 grams of oxygen on the bottom. Again, I'm canceling out my grams. The 16 comes from the periodic table. And on the top, I'll make it 1 mole of oxygen. That's what I want to change it to. I'm going to change it to moles. And it's always 1 mole, because 1 mole of oxygen weighs 16 grams. I'm going to do the same thing for nitrogen. So I know that 1 mole of nitrogen weighs 14 grams. Now for each of these, I'm going to clunk them out on my calculator. For oxygen, I got 3.9475. And for nitrogen, I got 2.6314. And I just had to stop these somewhere. I made sure that I collected at least my 4 digits, because each of these has 4 digits in it. I wanted to make sure I had 4 digits over here for each of these. If you don't do a good job at rounding off, sometimes you'll get extra errors in there and you'll make the problem unsolvable. So save as many digits as you can. Last step here, we're going to divide these two by the smallest to find their whole number ratio. The smallest value is the 2.6314 value here. So I'm going to divide both numbers by 2.6314. And when I did that on my calculator, of course here, I'm going to get 1. And up here, I get 1.67. So this is my ratio. It's 1.67 to 1. But it's not necessarily a whole number ratio. I need a whole number ratio. So since this contains some type of a fraction, the 1.67 contains a fraction. And in fact, upon this quick inspection, the 0.67 is around 2/3. So those of you who are kind of following me on that can kind of see, oh yeah, 2/3. 0.67 is 2/3. So this is like 1 2/3 to 1. What we want to do to get rid of this fraction and turn everything into whole numbers is we want to multiply this by a whole number that's going to eliminate the fraction completely. I suggest that we use either a 2, a 3, or a 4. Now, how do you know which one to use? Should I multiply by 2? Should I multiply by 3? By 4? How do you know? Well, you kind of inspect the fraction. And whatever is in the denominator of the fraction, that's the number that would be best to use. So in this case, it's 1.67, or 1 2/3. So I should multiply each of these by 3. Again, I want them to be in their same ratio, so I have to multiply both of them by 3. And when I do that, 1.67, or 1 2/3, times 3 is going to be equal to 5. And 1 times 3, of course, is just 3. So whoopee, I got these numbers now, 5 and 3. How does that end up being an empirical formula? Well, these numbers are going to be the subscripts in the formula. So for oxygen, I'm going to have a 5. And for nitrogen, I'm going to have a 3. So my formula for this particular compound is N3O5. Okay, so I have one that I'd like you to do. And I'm going to clear the board and show you the problem. And then I'd like you to work it out. So here's my new problem. I have a compound that's going to contain 40.05 grams of sulfur and 59.95 grams of oxygen. What's its empirical formula? We're going to go through the same steps. We're going to change it to grams, change it to moles, and divide by the smallest. In this case, though, notice that it's starting in grams. So what should I do about that? Do I need to change grams into grams? No. I'm just going to figure that this step is already done and just move on to the next one. Change it to moles. Why don't you start here? Change things to moles, divide by the smallest, pause the videotape, and then we'll compare notes. Okay, here's my answer. So you see I took each one, divided it by its mass found on the periodic table. So for this one, I ended up with the 1.247 here, 3.746. I chose the smallest, 1.247, divided both of them by that value, and I ended up with a 1:3 ratio, which became my empirical formula. SO3. Empirical formula